Well, welcome to our next lesson in Chapter 3 on properties of logarithmic functions. This is section 3.4 in your textbook. And today's learning targets, we are going to be adding some more properties of logarithms to our toolbox, and we're going to be using those to solve problems. We will also be using a change of base formula to evaluate logarithms, and that same change of base formula is going to help us to describe the graph transformations that occur. So let's go ahead and get started. First of all, the properties of logarithms. We have a couple of new properties that we're going to be studying. And the first property is called the product rule. And the product rule says that if we have two numbers that we're multiplying together and we're going to take the logarithm of a product of numbers, that's equal to the logarithm of each of those numbers added together. The quotient rule is very similar. If we have the logarithm of two numbers that are divided, then we subtract their logarithms. And the power rule says that if we have a logarithm of a number raised to a power or an expression raised to a power, that power comes outside or in front of the logarithm and gets multiplied. So let's go ahead and jump in and solve some problems using these three new properties of logarithms. One of the things, just to remind you, you may wish to review some of your exponent properties. I'm not going to cover that in the video. I just wanted to put a reference in here for you. In the very front cover of your textbook, there's a really good listing, a comprehensive listing of all of your exponent rules and also your radical expression rules. It would be a good idea for you to review those if you struggle to remember how to use those. So here's a few examples. We're going to jump right in. Use the properties of logarithms to write a sum or difference of logarithms. So in the first one, letter A, we have two things being multiplied together, and we also have one of them has an exponent. So we know from the product rule that the logarithm of two things multiplied together is the same as those two logarithms being added together. But now we can use the exponent rule to simplify the logarithm of y cubed. And remember, that said that whatever the exponent is just comes out front. So we have the log of x plus 3 times the log of y. And that's all we do to write that as a sum of logarithms. The second one, we're going to have a quotient here. We have a log of two expressions being divided. So we will be subtracting those. But then we have to deal with the exponents as well. So now the exponents just go out front. So this one becomes 2 times the log of 2x minus 4 times the log of y. And the third problem here, when we have a radical expression, remember that's going to be a fractional exponent. So we're going to go ahead and write that as an exponent, and then we also have a quotient in here, so we'll be subtracting. So we're going to write that as the natural log of x squared plus 5 in parentheses raised to the 1/2 power, because that's what the square root is equal to as an exponent. And then we're going to subtract from that the natural log of x. Well, we have a little bit of work to do with this first one. We want to bring that exponent out front. So that's going to be 1/2 the natural log of x squared plus 5 in parentheses minus the natural log of x. Now don't get confused when we have a sum of expressions inside here. We're not going to take the natural log again and bring this 2 out. Once you have parentheses around this and it's the natural log of something in parentheses, that's when you can stop. Some students get a little confused by that, and I'll probably address that a little bit more in class. So make sure that you understand once you have this expression, you can stop. All right, letter A, use the properties of logarithms. We're going to go backwards this time, and we're going to condense this. We're going to write the sum or difference of the logarithms as a single logarithm. So when we have a sum, we know that that really means it's a product. So that's the log of x times 5. Well, normally we write the number first, so that would be the same as the log of 5x. Similarly, we have the 2 times the natural log of y minus the natural log of x. When we have a difference, that means we're going to have a quotient. And the 2 out front means that that was an exponent for y. So that's the natural log of y squared divided by the natural log of x. So we could write that as a single logarithm as the natural log of y squared over x. All right, letter C. This one we have a 1/3 out front. Well, that must have been an exponent. when it began. So that is the common log of x to the 1/3 power. And if we wanted to write that in radical notation, that would be equivalent to the log of the cubed root of x. Either of these forms here is correct. Just watch your directions and see what form they would like your answer. This would be considered exponential notation. This one is called radical notation. If it's not specified, either is fine. All right, so your calculators, we've talked about this. We have a base 10 or a base e on your calculator. That's the only base your calculator can do. And sometimes we have logarithms that are in some other base. So the change of base formula allows us to use either base 10 or base e, we get to choose, to go ahead and evaluate logarithms that are in a different base. So for positive real numbers, a and b and x, and when a and b are not 1, we have this change of base formula. Make sure you write this down. It's the log of x to the base b, so the log of some number to any base. What you end up doing is taking the log of a base that you want. You choose the letter a, whatever base you want. Usually it's going to be a base 10 or a base e because that's what your calculator does. So it's the log of x divided by the log of b. And notice it's a new base. The base is a, and it's going to be either base 10 or base e from your calculator. So let's go ahead and do that. Let's apply that property. Let's apply this change of base formula to go ahead and solve or evaluate some logarithms that are not base 10 or base e. So the first one, we have log of 19 to the base 5. Well, our formula says take the log of 19 and divide it by the log of 5. And since I chose a common log, remember the common log, you don't write the base down. It's assumed to be a base 10. And the log of 19 divided by the log of 5. If you write that, or if you type that in on your calculator, that's approximately 1.829. So when you're doing these evaluating of logarithms, let's go to the nearest thousandth, which is 3 decimal places. Let's be consistent so that we all have the same answer. In letter B, we have the log of 10 divided by the log of 7. And when you figure that one out on your calculator, it's about 1.183. And would it matter, one of the questions I'd like to pose to you, does it matter if I'm doing the common log versus the natural log? And it makes absolutely no difference. You could take the natural log of 10 divided by the natural log of 7, and you'll get exactly the same value. So if you don't believe me, plug that into your calculator and double check it. Letter C, this one we're going to do the log of 2 divided by the log of 1/2. And the log of 1/2, I would just put that in as 0.5. And on your calculator, you will get a value of -1. The change of base formula also helps us to describe the graph transformations from the parent function. So here I have the log of x to the base b. Now just applying that change of base formula, that says take the natural log of x over the natural log of b. So we're changing the base to e. Remember, I'm using that change of base formula here, but this time I chose to use natural log instead of common log. So the natural log of x divided by the natural log of b. Well, we can write this because of our property of logarithms. We know that we could write this as 1 over the natural log of b here. I'm splitting this into 2 logs, and then the natural log of x, right? So this 1 over natural log of b, remember the base b, this is just going to be a real number. So 1 over the natural log of a number, that's a constant. That's just a number that you can plug into your calculator. So that tells us that every logarithmic function is a constant multiple. Remember, this is a constant, and it's a multiple of the natural log of x, which is a really cool thing. So when b is greater than 1, if that number is bigger than 1, we end up getting a vertical stretch or shrink by a factor of 1 over whatever that constant is. But if it's a fraction, we also have a reflection across the x-axis because it's outside the function. Okay, so we're multiplying by something outside the function, and it will be across the x-axis. And almost all the time, this is going to be a vertical shrink. You'll notice that in your problems, that it will come out to be a number less than 1, so it's a vertical shrink. So let's go ahead and look at some examples. So our instructions say to describe how to transform this function into, or transform the natural log of x into this function using that change of base formula? Well, we would take the natural log of x and divide it by the natural log of 3. And we would write that as 1 over the natural log of 3 times the natural log of x. Well, remember, this is a constant. You can actually plug into your calculator the natural log of 3 and take the reciprocal of that and get a value. When you do that, you get about 0.910 times the natural log of x. Well, now you can describe that. Once you have this constant value, that's a number less than 1, it's outside the function, so that tells us that that is a vertical shrink by a factor of 0.910. So there you have it. Go ahead and try this one on your own and pause the video and I'll give you the answer when you come back. All right, this one actually has 2 transformations, okay? So you're going to go ahead and write this one. It's 1 over the natural log of 1/4 multiplied by the natural log of x, same format using that change of base formula. Evaluate the natural log of 0.25 on your calculator and take the reciprocal. You get a constant value, a number of negative 0.721. Whenever you have this fractional value, you'll get a negative for your constant. And that represents that reflection that we talked about across the x-axis. So it's also a vertical shrink by a factor of 0.721 and a reflection across the x-axis. Here is your lesson check for this section. Go ahead and work on these on your own and bring your answers to class. We'll see you next time.